So section 2 is just talking about whether or not a reaction would occur naturally or if you would have to put energy into it. Thankfully, the methane and oxygen reaction doesn't happen unless we give it a spark, because otherwise, when we turn the gas valves on, it would just start burning spontaneously. So that's really what the second section is about, is whether or not something's going to happen spontaneously. So we're going to have to learn about how enthalpy change and entropy change in this concept of free energy. There's like 3 factors that all play into it, and we're going to have a table to decide whether or not a reaction happens spontaneously. So most chemical reactions are actually exothermic, meaning they give energy off, because the tendency would be for it to go to a lower energy state. That's why all those formations we see are negative, because if it was a positive number, you wouldn't likely have those things form. Most things want to go from a higher, everything wants to go from a higher energy state to a lower energy state. That's why we have to force things. Like if I didn't have this projector or lights, if I didn't have something hanging them up, they would just fall, because that's a higher energy state to a lower energy state. I had to do work to lift them up to go against their tendency to go to a lower energy state. There are some endothermic reactions that occur spontaneously because there's another factor involved that we need to talk about other than just enthalpy. One example would be melting. Melting takes in heat, and it does occur spontaneously at room temperature as energy gets transferred from a warm air to the ice. It's because what's happening is those water molecules, when they're in ice form, are very well ordered, arranged in crystals, and you go to this less ordered, kind of messy liquid phase. So a system can go from one state to another without an enthalpy change, but it will increase in this idea of entropy. And they're very, very similar sounding, but 2 different ideas. Enthalpy is really more talking about heat. Entropy is, we're talking about like order of things. So things tend to go to disorder. Entropy is that idea of disorder. So the disorder would increase. Here we have the decomposition of ammonium nitrate as a compound. It would decompose into nitrogen, water, and oxygen. Notice that on the left side we've got 2 moles. On the right side we've got a total of 3 moles of gas. So 2 here. So 3 moles total of gas and 4 moles of a liquid. So that arrangement on the right-hand side is more random, meaning the entropy increased. So it's less ordered than my nice 2 moles of solid crystals. Does that make sense? Like it's a lot messier. There's a lot more going on this side, more randomness on this side than there is when I have 2 moles of a solid. So that's why it favors the other side, because it's going to favor towards disorder. So that's that tendency I'm talking about for nature to proceed in a direction that increases the randomness. Think about it. If I just, you wouldn't be too happy with me if I just took that box of baking soda and threw it everywhere. But what would you expect to happen? Would you expect it to just be randomly all over the place? Or would you expect the Statue of David to form out of the baking soda? Probably the second one, right? But obviously, like, more orderly is less likely than more random. So that's what this idea, the tendency for things to go random, is called entropy. We can quantify that with this letter S. So the degree of randomness of the particles is entropy. Some examples. You can see that entropy change either goes positive or negative. Notice when I have like the breaking down of salt. So salt goes into its ions, that's increasing the randomness because it's in a solution now. But if I take solid sodium and chlorine gas and put it into a nice solid structure of salt, I'm now decreasing the randomness because salt is very ordered. The salt structure, the salt crystals, if we look at them under the microscope, they're like cubic, they're very nice and orderly. That's when we see a decrease in entropy. So the more random, the more entropy. The less random is the less entropy. That should say entropy up there. These are showing entropy, not enthalpy. Enthalpy is what we talked about last section. I think this might also mean to be entropy. And it goes back to solids, liquids, and gases. Which would have more entropy, solids, liquid, or gases? More entropy. So more disorder, in other words. Liquid would have more, but then gas would even have more, right? Because the solid is in a fixed position, they're close together, but then the gas is more random, higher entropy. And we have a table of these absolute entropies or molar entropies. That's kilojoules per mole Kelvin. The change in entropy, which can be measured, is, again, just like enthalpy, we did products minus the reactants. We can do the same with entropy. We can take the products minus the reactants, and we get, instead of delta H, we're getting this value delta S, which stands for the increase or decrease in entropy. So that's two factors. We have to look at enthalpy, we have to look at entropy, and then there's this other function called the Gibbs free energy, the G. So we're going to look at H, S, and G, and we're going to see how all those things combine to determine whether it's spontaneous or not. So the two things we're driven towards are lowest enthalpy, like I said. We want the lowest enthalpy, but we also want the largest entropy. So we want lowest energy, like the heat needs to be lower. We also want the more chaos is what's going to happen. So you want enthalpy to be low, so H is low, S is high, and the way to predict that is this Gibbs free energy. It combines both factors. And here's the formula. It also includes temperature. I should say all three factors because it also includes temperature. But the delta G, the Gibbs free energy change, is we take delta H minus temperature times delta S. So change in enthalpy minus temperature times change in entropy. And here's the table that we will be using to determine if it's spontaneous or not. So you're going to have to look at those three things. You're going to have to look at delta H, delta S, and T, and delta G once you do the calculation. So if delta H is negative and delta S is positive, delta G is negative, then the reaction is spontaneous. And you can use this chart on the test. But then if delta H is negative, delta S is negative, delta G can be either. The reaction is going to be spontaneous if T is less than this ratio. And we'll do some practice problems. I might just have you try them tomorrow, and then we will go over them the next day. But then delta H is positive, delta S is positive, delta G can be either. Then the reaction is spontaneous if T is greater than this ratio. But then if delta H is positive, delta S is negative, delta G is positive, then it's never spontaneous. So you're going to have to look at each of these values and figure out if it's spontaneous or not. It looks a lot worse than it is once we start seeing these values it's really not that bad. Again, to find delta G, you have to use this equation here. So you want to have that somewhere. The product of T delta S and delta G and delta H, they all have the same units. That's why this equation is able to work the way it is. And delta H and delta G can have positive or negatives. So that's why you have all these different combinations that we saw. So we can look at an example. We have ammonium chloride yields ammonium and hydrochloric acid at this temperature. So notice they give us a temperature, they give us a delta H, and they give us a delta S. So it's might not be as bad as you're thinking, because all we have to do is look at. So we know temperature is 298.15. Delta H is positive 176, and delta S is 0.285. So on my chart here, what am I missing? I have temperature, I have delta H, I have delta S. What else? What do I need to calculate? No, I don't have delta. Did you say delta H or? I said delta G. Yeah, delta G. Yeah, you're right, delta G. I just didn't hear you. So yeah, and they tell me that. They tell me to calculate delta G. So delta G, that's that formula. It's just delta H minus T delta S. I think that's simple algebra, right? Delta H minus T delta S. Just multiply these two. Take this minus that. So it's 176 minus 298.15 times 0.285. Forgot I don't have. Did you already figure it out? 91. You're probably right. Whoops. 285. Yep, 91. Good job. So that's all there is to it. We just now need to decide if it's spontaneous or not. And that just involves reading a chart. So this is 91 kilojoules per mole. So we look at it. Delta H is positive. Delta S is positive. Delta G is positive. What does that mean? So delta H is positive. So it could be either of these. Delta S is positive. So we're looking positive, positive, lots of positivity today. Delta H, delta S, delta G. We have to look at one other condition. Is T greater than delta H over delta S? So T is 298. What's that ratio again? It's delta H over delta S. So delta H over delta S is 176 over 0.285. 617. Yeah. So that's a clear comparison. 617. That is much higher than the temperature, right? So you got it. It's not spontaneous. No. Because the temperature would have to be greater than delta H over delta S.